something is proven useful for many different problems. We become familiar with that concept because of that, and this familiarity leads us to call it simple.
I'm very pleased to introduce Miles Kremer, who's an assistant professor in data and intensive science at the University of Cambridge. He's also a Schmidt Science Early Career Fellow and co-founder of the Polymathic AI Initiative, which is developing large-scale foundation models for science. So, over to you, Miles.
Thanks. So I left the title very vague so that I could kind of, choose what I'm going to cover last minute. So today I'm going to talk about, what is one of the most fundamental issues in machine learning for science, which is generalization and extrapolation. I'm going to talk about this in the context of foundation models and symbolic regression. So I want to start off with this kind of statement that Einstein's general relativity, it was published in 1915, but it's still accurate. It's predicted the correct dynamics of black hole event horizons, decades later. Yet standard machine learning models struggle even a little bit outside of their training data. And so this leads us to ask, why is physics so much better at generalizing than machine learning? Like, it's not even close, right? It's orders of magnitude better generalization. And I think this is a very deep problem, and I'm not promising that I'm going to kind of tell you the answer, but I have some ideas for how this could work. So to start off, I want to talk about Occam's razor. I'm going to talk about it in a way that you're probably not expecting. I'm going to kind of criticize it a bit. So Occam's razor involves this idea of simplicity. So a simple model is often regarded as better. But simplicity, like how do you define simplicity? Simplicity is a heuristic for kind of how well a model is expected to generalize. A simpler model is thought to generalize better. But what does that actually mean? What is simplicity? Like, if we really probe it, it kind of breaks down, and we discover that there's kind of no floor underneath us. So if I ask you, do you think adding two numbers, like 1 plus 2, is simple? I think like everybody would agree, adding two numbers is simple. But if I ask you why that is simple, it's a lot harder to define. It's kind of like one of these axioms in our heads, like, oh, addition is simple, therefore anything that is expressed in terms of addition is simple, but the simplicity of addition itself is kind of like left. There's not really like a motivating reason for that. So I want to explain how I think of this. So I think this is kind of the lie that we tell ourselves. So we say that a simple model is a useful model, but actually this isn't actually how it works. So in the history of human civilization, we've discovered a lot of mathematics from its usefulness. So addition is a useful operation. Even some animals know how to count, right? Even bees can count to 4. So it's this useful operation for many, many different tasks. Therefore, it becomes familiar to us, right? So it's a familiar operation because it's useful in so many different contexts. And then this simplicity label is kind of like a aesthetic quality that we assign it because we're familiar with it. But like we usually think of it as simplicity implies utility, but actually it's kind of like the opposite direction. Like I think what actually happens is that something is proven useful for many different problems. We become familiar with that concept because of that, and this familiarity leads us to call it simple. I think this is what is actually happening. And so the kind of general statement is that if something is useful for problems A, B, and C. Maybe a concept is used in different ways. If that's true, it's probably also useful for this new problem D. And so, I mean, I think this is kind of, I think it's interesting that, the world can kind of be described by composing concepts that are useful in other things. But I think the extrapolation problem exists, like this huge discrepancy between physics and machine learning, is because physics reuses concepts and traditional machine learning starts from scratch. So before foundation models were, in vogue, every time you train a neural network, you train it from scratch. You start, the universe from scratch. The neural network has to learn how to do everything. But a physics model, it has so many kind of core pieces that it's reusing that have been proven useful in other contexts. When a physicist writes down the model, they use operators, right? They use addition, multiplication, sine, exponential. These are core concepts that are useful in many different contexts. These operators were essentially discovered because they're useful for modeling the world. So like sine of x, it's used in like ancient astronomy, useful for wave mechanics, even things like a derivative, like a time derivative, useful for modeling anything that changes. So these are kind of very general concepts that are useful in many different things. So when you build a simple model, what you're really doing is reusing knowledge that has been validated across other problems. And so physics generalizes well, in part, I think, because it reuses proven useful building blocks. So we can kind of rephrase Occam's razor with this. So the traditional view is like this weird aesthetic quality that simple models are more likely to be true. But what's actually happening is that useful models are useful, right? You have some concept that's useful in many different things, and it's therefore probably useful in a new thing. So the models that survive, they're not, they're not kind of this like true simplicity of the universe. They're really the ones that keep working. So it's like simplicity, I don't even think it's like a real thing in some sense. Okay, so now back to machine learning. If we think about like machine learning and how machine learning generalizes, say I train a neural network. So I've got some neural network that kind of looks at X-rays of different hospital patients, and it classifies if they have pneumonia or not. So this is a paper from I think it was like 2016 maybe. It's like, it was really good at detecting pneumonia in hospital patients. But it turns out the network was not actually looking at the lungs at all. It was just reading this token in the background of the image that said which ward of the hospital they were in. And so this model has cheated. It's picked up on this artifact in the data. And in part because like the neural network, it's trained from scratch. It has no knowledge of other concepts. It has no common sense, right? It's trained from scratch. So this is kind of like, this is what we get as a result of that paradigm. So one perspective on this is in terms of symbolic regression, which is one of the areas I work on. Symbolic regression is a machine learning task where your objective is to find equations that optimize some objective. So you're trying to like fit equations to data. You typically solve this by optimizing accuracy of the equations in describing the data and also the complexity of the equations. And complexity here is just user-defined concept. So it might look like this. You have this equation, y equals z plus 2 sine z. You represent that as a tree of operators and variables and constants. This is also represented in data space, and we can compare this equation to data. And so symbolic regression, it's typically solved with genetic algorithms, and essentially you randomly mutate operators, maybe you crossbreed operators, so you kind of swap subtrees. Essentially, you're searching around in expression space for equations that fit data well. So you try to find something that fits the data well and is simple in terms of your basis. So it might look something like this in practice. So here's kind of like an example search. We're kind of searching all over these different trees, trying to find equations that fit the data. So this is symbolic regression. And we can see that in the end, we finally find something that fits the data. So the reason I bring this up is that I think symbolic regression has an insight to this problem I mentioned. Symbolic regression, it works best and it generalizes best when you are using operators that are common in your subfield. For example, in particle physics, they have this weird operator called a die logarithm. That makes a lot of sense in particle physics, and it's useful in many contexts, but it would never make sense in biology. It's kind of like a terrible choice in biology. We also find that expressions generalize better when they are smaller. I mean, this is kind of the standard Occam's razor idea. What's also cool is that if you train a neural network from scratch on some data and you fit a symbolic expression to that neural network, often you can get better generalization. So we have this package called SymTorch as one way to do this, but it's basically like you're kind of projecting the model you've learned onto a prior over function space that is like more appropriate for your problem. It could be because they kind of like align better with the patterns and concepts that exist in that domain. So if you're interested, so we have these packages, Pyser and SymTorch for doing this. So that's symbolic regression. So I think the really cool thing about this is that it's almost like a quantitative way to express this notion. Okay. It's almost like a quantitative way to describe this, in that I, as the user, have to define a basis of operators. I choose that basis using operators that I know are common in my field. That acts as a prior over function space. And it leads me to models that generalize better. That's symbolic regression. So the other perspective here is foundation models. And so people ask me, like, symbolic regression is these like tiny equations that you're finding. And then the complete other end of the spectrum is you're building these massive foundation models. Like, that seems kind of like why are you working on both? So actually I think that they're strongly connected, in that a foundation model is also exploiting this idea of reusing concepts. So there's been many talks today on foundation models, so I won't get into too many details, but the essential idea of a foundation model is that you have one general model that you've trained on large, diverse data sets for your domain, for example. You then take this model that has these like really good internal concepts, and you tune it to a specific task. So in this figure, it's like, okay, you have all of this text, all of this images. You train one model to rule them all, right? Like, it just predicts like the next word in the entire internet. It predicts images. It has this really good understanding of the structure of data. But when you tune it, you typically only do like one task that you tune to. When you talk to like ChatGPT, it is a foundation model that is trained on the entire internet, every book that's ever written, but then it's been tuned to follow instructions. And so I kind of consider like this model has learned these very general concepts internally that you are then exploiting when you tune it. And there's kind of like, I don't know if you can see it, but there's kind of a connection there to symbolic regression. So practically, like, why use foundation models? I mean, you get this universal improvement, or nearly universal, in prediction accuracy for many problems. Now, the downside is there's this large upfront training cost, but for specific users, there's a smaller downstream training cost. The connection between foundation models and symbolic regression is that symbolic regression is finding simple models in terms of the operators that you picked. So you know that addition is simple in my mind, multiplication is simple. You know, they're simple because they're useful. And then my symbolic regression algorithm is going to find models that are small in that basis. Foundation models are, you know, in some sense, they're these massive, opaque neural networks, but they both generalize very well. I think they're actually due to a similar reason, which is that symbolic regression is reusing knowledge in the form of mathematical operators, but foundation models are also reusing knowledge. It's just that that knowledge is kind of learned because they're, you know, training over many diverse data sources, but they're then using that knowledge for other problems. So I think there's actually this connection here that they exploit. So why does like ChatGPT Claude work? I think, you know, part of the reason is that there's these shared concepts across languages. So for the same reason that, you know, if you know Spanish and you know French, it's much easier to learn Italian because there's these shared grammatical structures and words. And so when you train a language model, it's kind of like exploiting these shared connections. It's learning like a common grammatical structure. It's learning common concepts. And this is why language models can, you know, they can generalize fairly well. Because of this, they've learned like these general concepts. I think we have the same thing in science. So in language, you know, many languages share this grammar, like they share grammatical structures. I think in science, we also have many shared concepts. Things like causality. It's shared among, you know, many sciences, dynamical systems, multi-scale dynamics, conservation laws. These are general concepts that are shared between many systems in science. And I think this is something that foundation model could exploit. Similar to how physics exploits mathematics as kind of like a, you know, it's prior knowledge. So we started this collaboration called Polymathic AI. It is this, oops, the part didn't render, but it's like this large international collaboration with teams at NYU and Cambridge. Basically, we're trying to pool compute resources to train models at something comparable to industry scale. I mean, it's nowhere near like language models, obviously, but it's, you know, we have a lot of compute for building these things. I just want to show this slide. So it's a big team. I think 2 people are also here. Payel is somewhere here. You can talk to her, and Alessandra might be as well. But this is kind of the team. So I want to go through a little bit about Polymathic's, I guess, kind of the path to our current state. So in 2023, we started with some ideas to kind of prototype this. So we were curious, like, can this foundation model idea really work in the physical sciences? So this was one of our first papers called Multiple Physics Pretraining. So this is a single model. It's a single transformer model that can take in many different physics. So these are like physics simulations. And it can predict the next step in all of these different physical simulations. And we found that, perhaps not unexpectedly, training this one model on multiple physics helps it in downstream tasks. So, for example, if you train this model on advection, the advection equation, you train it on diffusion equation, then it needs much less data to solve the advection diffusion equation. So you see here the green curve, that's a model trained from scratch, and the blue curve is pre-trained. So it needs much less data to reach the same error, which is like, it doesn't seem that crazy to me. I mean, maybe it was unusual several years ago, but this seems kind of like expected. What was really unexpected, though, is kind of how far we've seen this work. Because the one question that we always get is, like, how close does that physical system have to be to your model? What we found is, so in this plot, this is the multiple physics pre-training transformer. It's been trained on many different physical systems. And then this is the amount of data that you give it for a new task it hasn't seen, like a new physical system. The blue model is the pre-trained model. So this has seen like many different fluid dynamics scenarios, and it needs the least amount of data, which isn't crazy. The green is the model trained from scratch. So that's a model, it's like a toddler, it's like a baby, like it's never seen anything, it doesn't understand how the world works. It's just trained on this specific problem. So that needs a lot of data to get to the same level. Now, the really interesting thing is the middle. So the red and orange curves, these are models that are trained in part on cat videos. So this model is literally trained on like videos of humans petting cats, and it literally gives you better performance than training from scratch. And it's quite significant in some places. And so I remember this went kind of, there was this tweet that went viral at the time, like, oh my God, like pre-training on cat videos is like state-of-the-art turbulence model, which is kind of true. Like it is, it could be due to like a significant thing, like the spatiotemporal continuity of cat videos informs the spatiotemporal continuity of like eddies in fluid turbulence, right? It could be something dumb, like you train the model on any task and it just like moves the weights into a better space. I mean, I like to think of it as like, cats don't teleport, neither do eddies, therefore there's like transfer, I don't know. But yeah, I mean, this is something we made, I think, to kind of preempt like a reviewer question, like, oh, how far does this work? And we were expecting it to fail, and it didn't, which was kind of crazy. So basically, this is like, we found this very promising, and so this kind of like, pushed us forward. So we did this like Astro Model 2. This was, just contrastive learning, image spectra, and then you kind of adapt from the embedding space. So I think, yeah. So I won't talk too much about that. I think, there's great early work. So Anna's talk, talked a lot about this, like Zubot model for multitask pre-training, and there's other work on generative models for Astro data. So it's kind of like known in Astro that pre-training helps. So the major bottleneck for us at the time seemed to be like the data. So there's many different data sets that exist, but the challenge for us is putting them in a uniform format. So what we did next in 2024 is data set aggregation formatting. So we released these two data sets. So one is called the Well. This is physics simulations in 16 different physical settings. So some of these settings, they don't even have density. They're like two chemical species. Other systems are, fluid on a sphere. Like it's this very diverse data set of different physics. The multimodal universe is, these are existing astronomical survey data. It's just kind of formatted in a way that's easier to use. So those were big collaborations, and that was kind of like a large part of 2024 was building these data sets. So 2025, so this is really when we started trying to build these things at full scale. So one is called Walrus. I'm going to talk about this a bit. So Payel is here, who's co-lead of Walrus, if you want to chat with her. This is, it's a fairly large model. It's trained for a week on about 96 H100s, which, it's definitely not the scale of language models, but it's, for academics, it's hard to get this sort of thing set up. Walrus it's a foundation model for next step prediction. So you give it a physics simulation, you give it 5 previous states. So it's like, okay, this is the fluid at time step t-1, t-2, t-3, and you try to predict the next state. So give me t. And you basically just train this prediction problem on many different physics simulations. So like everything in the well, for example. The architecture itself, it is a transformer. It's basically like a video foundation model. So there's this temporal attention step and a spatial attention step. These are separated as kind of like an efficiency trick. There's also like many other architectural tricks. I'm not going to go into detail about all of this, but they're described in the paper. So we have this like adaptive compute patching, which is useful. So if you have like more compute, you can kind of increase the resolution inside the model. And there's a bunch of different tricks for like spatial equivariance and that sort of thing. So this is Walrus. This is what it looks like. So these are different predictions. These are kind of the range of the different physics that this model can handle. You'll notice that some of them are 2D and 3D. So the model's actually trained on both. So it can handle both 2D systems and 3D systems with the same kernels. So it's the same like internal dynamics, but it works for both 2D and 3D. And so the predictions are quite good. What we're doing now is kind of the downstream tasks. So these are kind of, these are different like large scale simulations that are really expensive to run. So for example, this red supergiant simulation, I think I forget how many, it's like, there's only 3 of these simulations in the world. They're really, really expensive to run. But you can tune Walrus on these simulations, and then it can just generate it, in an hour, right? Like it can just generate it really quickly with pretty good accuracy. So there is this trade-off, like when you build one of these surrogate models, you are going to lose a little bit of accuracy. That's almost always going to happen. But you gain a lot in terms of efficiency. The other model is called ION. So this is another astronomical foundation model. This one's really scaled to push large amounts of data, large model scale. So it essentially learns the joint embeddings for 100 million different galaxies and stars by basically like the basic way it works is you have this large transformer that is trained to predict the missing data in a given data set. So it's this very, general objective similar to LLMs where you just like mask part of your data and you try to fill it back in. So you mask this word, you try to predict it. You mask this word, you try to predict it. You do this for all the images we have, all the spectra we have, physical parameters, segmentation maps, and you do this across modalities too. So you give it like an image modality, you ask for the spectra. You give it half an image, half a spectra, you ask for the other half of each. So there's this infinite combination of different ways you can predict it. And by training the model on this, you've given it this very general internal representation. So the approach that this uses is called 4M. So it's a 4M style transformer. The way it works is the model itself is an encoder-decoder, so the old school style of transformer. It is trained to predict the missing parts of your data. So the first step is for each modality you have, say you have like an image modality, you have a spectra modality, you train a tokenizer for each modality. So you could essentially think of it as like an autoencoder. You train an autoencoder for each modality you have. Train an autoencoder for images, an autoencoder for spectra. These autoencoders, they get quantized. So you have these embedding vectors, and you find basically like the minimal set of embedding vectors that can describe any image. This essentially gives you a tokenizer just like a language model, because now all of your data is just like mapped to tokens. So now you've got essentially this token prediction problem, which is this very general learning problem. And you randomly choose some of those tokens and you predict the other ones. So you have an image and a spectra for a given galaxy. You get 4 tokens for the spectra, you get 9 tokens for the image, and you just like predict the held out ones. You try to predict those. This gives the model a really good internal representation. And you get like nearly universal improvement on standard machine learning tasks in astronomy. So you take like a standard supervised machine learning pipeline, and it just, it's really hard to train it on like 100 data points. But the foundation model, even though it's like a new task, it just has like a better, it's like it speaks the language of the data. Like it already understands the core features here. And so you can kind of generalize much better. You see, even at the data rich end, like there's this gap between the supervised method and the foundation model. Once you have these embeddings, you can do a lot of cool stuff. So this is one of our interns, Nolan. He built this thing called Ion Search, which is essentially this text-based search engine for galaxies. It's similar to Anna's model. This is trained on Galaxy Zoo, which is kind of like aligning embeddings. So you align like text embeddings with image embeddings. So this also uses like open source LLMs to kind of bootstrap explanations. Once you have this, you can literally just like type in, the type of data you want. So this is like, I search for a face-on spiral with ring-like structure around a core. And it finds all of these galaxies that kind of match. And again, this is using the embeddings, right? It's not like using, oops, let me do this. It's not like it's using the, like a language model embeddings. It's actually using the foundation model's embeddings that are aligned with text. And so you can see, and the other cool thing that Nolan built is you can do a search for similar, which is just like in like Google Images, right? Like Google Images has this like show me related images. So you can do that with this. So you see here, we have this text query, and then we also have this image query. So we're like embedding a text vector, and then we've also got this image embedding, and we sum them. So it's the summation of the text embedding and the image embedding, and this essentially lets you refine the search. So you can also like upweight the image embedding, and search for galaxies that maybe are close to that one. You can also do it like negative, so search for stuff that doesn't match it. But it's surprising like how well this works. Like, I think he was like, I don't know, he did a search for like streams, and it was like, it found streams that we didn't even know about. So like a stellar stream is a type of object. Yeah, I mean, I think there's a lot of cool stuff you can do with this kind of model. You can also use it. I did warn him that I was going to talk about this, and he says he doesn't think it will crash. So you can try it. You can try to. I told him like, we're not DDoSing you. I just showed this link. Okay, so I don't have too much time left, but I guess on the interpretation side, so I've talked about how symbolic regression is reusing concepts that we know are useful, like mathematics. Foundation models kind of learn concepts that are generally useful. But are the concepts a foundation model learns like actually physical, or is it just like weird artifacts of the data? So we have been investigating this. So this is a project led by Rio Fier, who's one of my PhD students. We wanted to understand how our physics foundation model represents vortices internally, like a fluid eddy. How does it represent that? The way we attacked this is that we kind of separate our data. Some of the data has a vortex, and some of the data does not have a vortex. This is a specific data set, by the way. We then inspect the internal dynamics of the model in each setting. It's almost like you show, I don't know, you show someone a scary movie and you're like measuring their neurons, and then you show them a happy movie and you measure their neurons. It's basically like what we're doing, but with fluid eddies. It's this really simple concept from the language model literature, which is you measure the average activation vector. So you compute the vectors or the activations inside your model. You average those for when the physics feature's there, when it's not there. You take the delta between them. So you get this direction in activation space that essentially represents like how the model sees that feature. You can then inject that and steer it. So you take the current activations, you add that vector in, and it's almost like you're poking someone's neurons to trigger a response. And it kind of works like, oops. So this is suppressing the vortex, and this is amplifying the vortex. And it's kind of cool. Like, it's literally just a linear direction. It's just a single vector, and it captures this fairly abstract concept inside the model. We can also like inspect the other fields, and it kind of looks like, oh yeah, the model is actually generating the correct physics to produce a vortex. The other thing we investigated is like, I mentioned that we figured out this feature from just one data set. But this is a foundation model. It works on many different data sets. So in principle, we could kind of transfer that vector over. So we did that, and it also works here. So this is the gas mixing data set, and the right side is when we amplify the vortex, and the left side is when we suppress the vortex. So it's like when you subtract the vector. And you can see the right side, it gets, it has many more little eddies showing up. This even works for data sets that don't even have fluids. So this is the reaction diffusion data set, which is like two chemical species reacting. And I don't know how, but the model kind of figured out like, oh, I'm going to make the chemical species like start swirling around. Even though it literally doesn't have density, it doesn't have velocity, it kind of transferred. So to us, this tells us that maybe the model kind of figured out like this abstract physical concept and is kind of representing it like as a shared direction in activation space. We did this for other physical concepts like This is diffusion, which also works quite well. This is like suppressing diffusion. This is, okay, these are just like other ones. These are speed, but it basically like works in many different contexts. Okay, so I'm out of time, so I'll just give shout outs. So this is our local team of PhD students and everyone. And then this is, so these are other grad students. And then this is the Polymathic team. Many other collaborators not shown. Okay, takeaways. I mean, I think it's true that simple models extrapolate better. I think what's really interesting is that the definition of simplicity, like we treat it as an aesthetic, like almost like psychological quality, but it's really in terms of useful concepts and like reusing useful concepts. And I think foundation models actually learn generally useful concepts. So I think they're basically maybe the current best way to fix this generalization problem in science. So I'll stop there. Okay, thanks.